Good morning. So we're starting into some new material today, going from kinematics, the study of motion, into dynamics, which is the study of the forces that cause a motion. And so one of the first things we need to talk about is what is a force? A lot of you guys probably have an idea. Certainly not the force from Star Wars, but probably in the simplest sense, a force is basically just a push or a pull. So something that's going to create some motion. And if I have an object at rest, so let's look at this shopping cart full of, it looks like watermelons. Um, Initially, that cart is going to be at rest, just sitting there. And if we wanted to get it moving, obviously we're going to have to apply a force to it. And so to measure the magnitude of a force, we are typically going to use what's called a spring scale. So in this picture, you attach a spring scale to an object, and um, the force is applied. In this case, it'd be a tension force, and it's going to stretch a spring inside the scale, and that's going to be calibrated to measure a force in newtons. So one of the first key ideas is that forces are measured in the SI unit of force, which is the Newton, which is a kilogram multiplied by a meter per second squared. And I'll get to where that comes from here in just a minute. So think back to middle school physical science, probably the last time you guys have talked about Newton's laws. We'll quickly refresh Newton's laws, and then really the focus of today is to learn how to do something called drawing a free body diagram. So it's how we analyze forces acting on objects in physics. So first law in one word is called inertia. And you might be familiar with objects at rest, stay at rest, objects in motion tend to remain in motion unless acted on by a force. And so what does inertia mean? Inertia is this, it's actually a measurement measured in kilograms, and really it's mass, and it's a tendency for an object to want to remain at rest or to remain in motion. So if I have an object that has really large inertia or mass, it's going to be hard to get it to move. And if I have a semi, which also has a large inertia and it's already moving down the highway, it's going to be hard to bring that object to a stop. And so that's basically what Newton's law says. Interesting thing, in a vacuum or in outer space, if I have an object that's in motion, Newton's law is definitely going to be important because that object is going to want to remain in motion forever. Basically, objects in a vacuum in outer space just kind of keep traveling at whatever speed they're traveling at because there's nothing to slow the object down. Uh, Newton's second law, oh wait, nope, we're still on first law. Inertial reference frames. Okay, important thing. Inertial reference frame is, well, first let's talk about reference frame. Reference frame is a point of view to see the motion. There are certain points of view where Newton's first law is apparently violated. So this is rotating or accelerating reference frames. For example, okay, imagine for a minute that you are sitting in a train and the train is accelerating, and you look out the window and you see a ball sitting there on the ground. As you are in an accelerating reference frame, the ball appears to be moving backwards with respect to your point of view. And apparently it looks like it's violating Newton's first law. It looks like it's not remaining at rest. Looks like it's moving with respect to you. So because of what you're doing, it appears that Newton's law is no longer valid. So for the most part, we got to consider the reference frame. Similar kind of example with rotating reference frames. But for the most part, Newton's first law is always going to be valid. So, how does mass work into this? Mass, like I said, is the measure of inertia. It's measured in kilograms. Mass is not weight. Huge misconception. Students and sometimes teachers will use mass and weight interchangeably because we can kind of get away with it because we're not really moving to different planets. But think of it this way, to add mass, you literally have to add molecules, or you can subtract molecules to subtract mass. Weight is a force. So forces are the product of a mass and for the most part, how the gravitational field is acting on that mass. So on planet Earth, we use our mass in kilograms and we multiply times the acceleration due to gravity, which we already learned about, which was 9.8. So if you ever want to find the weight of an object on Earth, you simply take the object's mass in kilograms and multiply it by the acceleration due to gravity, otherwise known as the gravitational field constant of 9.8 meters per second squared. And then you get a kilogram multiplied by a meter per second squared, which turns out to be a Newton. So mass versus weight, don't get those mixed up. If you go to the moon, the field is a sixth of that on planet Earth, and therefore your weight will be much less. However, the only way to decrease your mass is to diet and exercise or lose a limb. Let's hope that doesn't happen. Okay, so second law. Second law is basically just an equation that relates net force to mass and acceleration of an object. And if you look at the equation here, there's a summation symbol, which means the sum of the forces, and that is super, super, super important. And let me take a moment to illustrate what I'm talking about here. Now it's a pretty good time to talk about free body diagrams, and we're going to illustrate what this net force business is. So Newton's second law, written as the sum of the forces equals an object's mass multiplied by its acceleration. So what's the deal with this sum of the forces? So a free body diagram is a way to examine the forces acting on an object, especially when we have more than one force acting. And so what you do is you start by drawing the object as a dot. So this is going to be a really simple free body diagram for an object, could be you, sitting on a flat surface. And so the object is represented by a dot, and the forces are drawn as arrows coming off the dot. And so, all objects experience a weight force due to gravity, and we capitalize the type of force. So there's a lot of different kinds of forces we'll go through, but for now, the weight force is the force acting down caused by gravity. And we're going to write a couple subscripts, so some notation to indicate who is doing the force and what is the force being acted on. So the weight force is being generated by the Earth, and then it is acting on. Okay, so you got to figure out, well, what's the dot? Could be table, could be you. For this example, I'm looking at this document camera, so I'm going to say the weight of the weight force created by planet Earth acting on the document camera. And when we first do free body diagrams, we'll use this notation until we get proficient at it, and then we can kind of forget about it, and we'll just be writing the force values. But for now, I want you to capital letter for the type of force, who is doing the force, so by, and what is the force being acted on? So by force type by comma on. And so that's the length of the vector here, the force vector indicates the magnitude of the force. I didn't weigh the document camera, so we're going to leave it as a conceptual model here. But if we did know the magnitude, we would put a little equals, and then let's say it's like 5 newtons down or something like that. But when I look at an object with just one force vector on it, that right there tells me that the forces are not balanced. It tells me that, okay, only one force is acting. There has to be something called a net force. So the net force is simply the sum of the forces acting on an object. So if that's the only force acting on the object, it means there's nothing supporting the document camera. That picture I've drawn there would be a free body diagram of the document camera in free fall. It would be accelerating at 9.8 down. It would also have a weight force, which is what's pulling it down. And the weight force is not going to be, the 9.8 meters per second squared. It's going to be a value in newtons. And so right now what we can do is we can find out, okay, if I know the weight force of the document camera is 5 newtons, I could figure out what the mass of the document camera is. Now remember, I made that number up. But basically the weight is equal to mg. Now that looks a lot like Newton's second law, and it should. We've got the force equal to the mass times the object's acceleration. So we know the acceleration of the document camera in free fall is 9.8 meters per second squared. We want to know what's the mass of the document camera, and I said that the force, the weight force, was 5 newtons. So we would divide 5 by 9.8 to solve for the mass of the document camera. And that's not correct because I don't know what the mass is. But anyways, that's not the point of this. The point of this is the document camera is not accelerating in free fall. It's just sitting there. So there's got to be a force back up which is supporting the weight of the document camera. And that force is going to be a different kind of force. I'm going to introduce something called the normal force, written as capital N. So normal forces are pushing forces that are perpendicular to an object, and they can be applied by pretty much anything. So when I say normal, just think like push. And who's doing the push? Well, I see one thing touching the document camera. I see the table as the agent of the force, and I also see the document camera, which is the object that the force is acting on. So I'll put D. So the second subscript should be the same because we're drawing a free body diagram on just this one object. And so both of those two forces are balanced. And what does that mean? In this case, it means the net force equals 0. Okay. And that means that the acceleration also has to be 0. Still have a mass, but we get no acceleration if we have a balanced free body diagram. That is a key idea. So if you learn one thing from this video, balanced free body diagrams mean 0 acceleration. Imbalanced free body diagrams mean there is some sort of acceleration. You got to have acceleration. Now, think about this question for 1 second. Could I have an object that is moving yet still have a balanced free body diagram? Okay, what did you come up with there?